All right, everyone. Good afternoon. We're glad you could join us today. Just before we go ahead and get started, just a few housekeeping notes. We ask initially if you could mute yourself. Sometimes background noise can be a bit of a problem since we're recording this, and we'll hopefully use this recording and add it to the XSEDE allocation pages for others that weren't able to join us to see. Along the way, while we're speaking, if you want to put questions in the chat box, several of us will be following along. And then once we get towards the through most of the talk, we can possibly go back to mics and ask some questions, and we can have some nice discussion. So it should work out pretty well. So let me introduce the three of us. Dr. Jay Alameda from the University of Illinois, the NCSA Center, as part of the ECSS allocation or ECSS education group, helps us with all of this. Dr. Lars Kostriki from Texas Advanced Computation Center is going to give the brunt of the discussion of code performance and scaling. And myself, Ken Hackworth, I oversee the XSEDE allocations process. And we'll give you a few initial slides and be happy to answer any questions along the way about allocations and this process that you're interested in. So if we can go ahead for the next slide. So as this is an XSEDE function, we have a code of conduct that we'd like to stick to. So for this function, we ask that you all be, considerate of everything here. If you have any questions or concerns, you can read the code of conduct in full there with the URL listed. I am the event organizer as well as an ombudsman for the code of conduct with the XSEDE program. So if you have any concerns or anything like that, you can always reach out to myself and we can discuss. But let's hope everything goes well and we won't have to deal with that. The next thing is words matter. So the XSEDE program has worked very, very hard to work on words and terminology and all that so that it's comfortable for everyone. So along the way, in any XSEDE program, if you see something that's concerning to you, you can always send email to terminology@xsede.org. You can do it anonymously if you'd like. Let us know if there's something that you're uncomfortable with in terminology, words, whatnot, in any functions, and we can get back to you on that. So XSEDE, Extreme Science and Engineering Discovery Environment. So we're here to substantially enhance the productivity of a growing community of scholars, researchers, and engineers through access to advanced digital services that support open research and coordinate and add significant value to the leading cyber infrastructure resources funded by the NSF and other agencies. So that is our mission, to help you all get science done. And that's what we're here today, to help you with your proposals and your code performance and scaling to use efficient resources on these digital services. So we provide these with seamless integration to these different NSF funded resources across the XSEDE landscape. They're not owned by XSEDE, they are owned by the different site in question, but XSEDE allocates them for the foundation of the national cyber infrastructure ecosystem. So connecting to these digital services, we have a diverse portfolio of resources that we offer: HPC systems, high throughput systems, GPU and AI systems, visualization, large memory systems, data storage cloud systems, and then we also have the ECSS group and the GCI group. So some of us, Lars and Jay, are part of the ECSS group, but these are US-based. These are for US-based researchers who are eligible. There's no cost for these researchers to use these resources. We do recommend that if you don't have a startup allocation, we recommend that you do get one of these to get your feet wet on these different resources. And then that'll allow you to get to know the machines, do some scaling and benchmarking, testing of codes, your own codes, third-party codes. And then you can graduate to the larger production allocations, or we call them research allocations. And that's especially what this topic is for, the code performance and scaling that is a necessary document to be included in a research allocation request. Next slide. So why request a startup allocation? And I quickly detail it. So we will receive these or accept these at any time. There's no deadlines. These were reviewed fairly quickly we try to say less than 2 weeks, but we're usually 9-10 days is our average, so some can move fast. With an open submission window now that opens September 15th for research requests, if you need to do benchmarking and code performance scaling, you'll want to get them in quickly, and you'll probably want to reach out to us by sending an email to help@xsede.org. That you're sort of in a rush. We can expedite some things. The very simple, just a CV for the PI, an extended abstract is all that's needed. Again, this is to be doing testing, get your feet wet, initially getting started with some research, but really for benchmarking and getting code performance and scaling information. Then this will lead to research allocations where there is no limits on requests that you can ask for. If you need 10 million, you can request 10 million. We'll do our best to award 10 million, but you got to go through the startup phase. You have to prepare the right information, full proposals. These are reviewed quarterly by a panel of peer reviewers. You can have one PI or one award per PI or research team. We see over 200 proposals per quarter, so it's very high. It's highly competitive. Proposal quality matters. And here, what we're talking about is this code performance and scaling is an essential piece of these proposals so that we can make sure that the requests are justified and that the research team can use these resources efficiently. Okay, and this is Lars' start. So thank you, everyone, and please ask questions in the chat to begin, and we'll carry on towards the end with some discussion.
Yeah, thank you very much, Ken. Yeah, my name is Lars. I'm going to give the rest of the presentation, and that is about how to write a proposal. You can say it's completely self-serving. We are all members of the review committee, and as you all know, reviewing good proposals is so much easier than reviewing proposals that are not so good. So us helping you writing a better proposal helps everybody to be more productive and get more done. If you have a question that relates directly to what I'm explaining on a slide, you can also unmute and we make it more lively and we have a discussion. You can put it in the chat and then I will pick it up, or we punt it to the end of the talk, so we can go through all general questions and we can also go through all specific questions that you have for your individual plans, but the individual questions have to be at the end, obviously. Yeah, I've been a long time TAG member, and I am also one of the leads for the Frontera reviews process. So basically all I'm saying here also applies to Frontera if you think about applying there as well. So the big thing is you have to write a proposal, 10 pages, and it is very similar to other proposals that you have submitted. But here now the audience is different, the target is different, and at the center of your document is a well-justified document, a computational plan. And so it is like a normal proposal, but it is not your NSF proposal and then 3 sentences added to, we need some resources. It's kind of the other way around. The science is important, but the reviewers focus on the computational plan. And if your computational plan doesn't pass the test, then the science doesn't really matter. And what we are all looking for is that you're demonstrating that you know what you're doing, that you can use the resources in a responsible, effective, and efficient manner, and so on. And so this will be about how to write this computational plan. And throughout my presentation, I have a lot of hands-on advice that I put into these orange boxes. And of course, not all advice applies to every proposal or all of you. So you just pick and choose and, apply some common sense there. You're getting started with a startup, and you use that to produce data that you then provide in your document, scaling data, performance data. You can do that anytime. It's really simple. When I talk to users one-on-one, I tell them, hey, it's 4 or 5 sentences, field of science, your work, and what you want to do. And in terms of what you want to do, it can be anything. It can be running software that you ran before on other system. It can be developing software. It can be just, I want to get my feet wet. Anything goes into that, in that category. So it's really only a few sentences. And you get some amount to get started. You can also ask for other, non-CPU hardware like GPUs or Hadoop systems. And of course, AI is a big part of the story nowadays. And then from a startup, you promote this whole thing to a full proposal. And you use a lot of common sense when you write this proposal, like in any other competition. New groups are under more scrutiny than proposals from well-established groups. If you are well-established, you have a better chance of winning very large grants. And if you are new to this, you should establish a track record first. Don't worry if your proposal gets rejected the first time, you will get hopefully some useful advice in the review, and then 3 months later you resubmit and you will be just fine. You should also have a rough idea of how large the resource is and then compare your request size to the total availability of the resource. I put that into the common sense category. You know how many hours there are in a year, and you know how many nodes there are in the resource, and you know how much you want to request. There's a 4th bullet point that I should have added. I realized that last time. There was, of course, one proposal that I reviewed where the size of the proposal was, if I remember correctly, 3% of the resource, and 3%, that is pretty large. I mean, these resources are used by hundreds of researchers. 3%, okay, that was fine. But the PI didn't apply common sense. We award resources 4 times a year. So what you have to compare it against is a quarter of the system. And that elevated the 3% to 12%, and that was certainly out of the question. If we award at that size, then basically only 10, 15 groups would get any funding. Smaller requests, less scrutiny than larger requests. Focus on what you really need. There are a lot of resources that are very similar in XSEDE, all the big clusters, all the big CPU clusters, and also all the big GPU clusters. They are all very similar. Do not target similar resources without a good reason. What is not a good reason? The system may be down, or I don't like the queue time. That is just not a valid reason. The downtime on our systems is very, very low, of the order of 1%, usually for preventive maintenance, and then that there are queues and that there's queue time. That's just a fact of life. You cannot avoid that. Pick a reasonable size. Acknowledge to yourself that there is a competition for these resources. Don't be overly ambitious. And if you know that there's a competition, you know that if you put in some effort, your proposal will do significantly better. What makes a good proposal? You're competing with many other outstanding resources. Better proposal pays off. Description of science, detailing the specific scientific questions so that the reviewer can see, are the computations that you're proposing are really solving a specific question, stuff like that. You describe a little bit the software, how it is parallelized, how you want to use it, and then highlighted here the computational plan, which with scaling. And then from there, you estimate the number of SUs. And the rest of my talk will be around those points 4 and 5. And the supporting data Oops, there must be a word missing. I think that was missing last time. I really have to fix that slide. The supporting data, the scaling, and to demonstrate the computational efficiency of your application or the code you want to use. That comes from previous allocations, or if you're new, from your startup. And it may come from other similar systems, but they have to be really similar. Otherwise, you will run into problems. I will go into some details there. Some details here on the right. You have to focus on the computational plan. The reviewers are not necessarily domain experts. So if your proposal is in chemistry, other chemists may review your proposal, but they are not necessarily domain experts in this niche where your chemistry happens. Same as for physics. You're an astrophysics and there's a solid state physicist. So you have to explain a little bit what is going on. A broader approach is appreciated. Connect your scientific questions to the computations and describe a little bit what equations or algorithms you are using, and particularly how the code is parallelized and stuff like that. I mean, we don't put too much detail there, but some information, particularly parallelization, is interesting. And then if it is homegrown code, then you would describe different things than if you if you are using well-known community code. But in any case, there should be something. Assure the reviewer that you are familiar with the software, that you know what's going on here. Present a computational plan, and it has to have some details. The number of calculations you want to do, and the runtime, and how large these calculations are, the node count, and how that relates to your scaling data. All details to come. And with all that, I will go into some details how to now use some basic math to put all the pieces together so that you can come up with the total SU estimate in a way that the reviewers can follow that and verify your number. And scaling is then being used to prove that you use the resources efficiently, that your code is efficient, that your application is efficient, and then from there you calculate the number of SUs. And that we go into lots of details there. Computational plan has center stage. Just don't have a normal proposal and add one sentence. We request some million SUs, and then we will do something, and some proteins will be folded or some galaxies will be analyzed. That is just not enough. Okay, we are using scaling to demonstrate efficient use of the resource. We all know that it is difficult to judge the efficiency of an application. The scaling is a proxy. It's not a very good proxy, but it's the best proxy we have. If you really want to delve in how efficient a certain application is, then you would also review the algorithm, competitors, all kind of stuff. That is way too complicated, and for many applications that's not even really a good answer. In the end, for some application, it's just as fast as it is, and sufficient steps have been undertaken to get the best performance out of it. So scaling efficiency is a proxy. And of course, we like to see the scaling efficiency on the target system or a similar XSEDE system. If you're using a different system, it has to be really similar, and it cannot be just an old system and then you scale the SUs with some fudge factor. Those numbers can go horribly wrong. And the larger your request is, the more stringent that requirement becomes. And you present, of course, scaling for a typical case, for a few time steps, for a smaller sample, and not all situations are clear cut. So if you do, for example, adaptive mesh refinement, you have to be a little bit more creative, choose the simplified setup, discuss the implications. All the reviewers are familiar with all this. You just have to put in the effort. Your scaling document should either cover the number of nodes targeted for production, or be at a point where you can apply a well-justified extrapolation from a smaller sample to the sample you really want to target. And you will target, of course, a node count for production where the scaling is good. And we will go into details what is good scaling, or what is scaling at all, and then what is good scaling. And you balance wall clock time against scaling and parallel efficiency, staying on the side of efficiency, not convenience. So scaling can be presented in multiple ways. There are in principle 2 experiments that you can run. One is called strong scaling, one is called weak scaling. Strong scaling means the workload is constant, and now you add more and more resources. As you add more and more resources, you would expect that your wall clock time decreases, your execution time decreases with number of resources, and now you plot this ratio of times. And preferably you will plot T1 over Tn so that you get an actual speed up. So n larger than 1, you get a number that is larger than 1 because here the denominator is decreasing. And now the ideal strong scaling is a linear relationship, and hence easy to assess. And don't do the opposite where it is 1 over x. I have a graph in a minute. Usually linear axes are chosen. So do lin or log, but don't do lin log, because then things get a little bit screwy for strong scaling. Sometimes you do strong scaling experiment on a single node. Reviewers, of course, know that scaling will flatten on a single node. Most applications are memory bandwidth bound, and the memory bandwidth will be exhausted to a large degree already before all the cores are utilized. Reviewers know that. If you see that, if you have such a diagram, just explain it a little bit, but you don't have to go into too many details there. It's often conducted, of course, for smaller calculations on single nodes or on a few nodes. Here's an example how it would look like. You make the reviewer's job easy by having the ideal scaling being a linear relationship. Good scaling is here, reasonable scaling is there. Bad scaling starts where you deviate significantly from the ideal line. Nobody would pick something where the performance drops, but there's a surprising number of PIs who picks a number where the speed is maximum, but where also the waste is maximum. So if you go from here to the left, you have to wait a little bit longer, but you're not using that many resources, so other researchers can do their research. So just your convenience is not at the center here. And if you go with 1 over x, then you have a 1 over x curve, and here it is difficult to assess scaling, and hence the reviewers will be not happy. I have reviewed hundreds of proposals, of course. I'm willing to put in some effort in understanding the data, of course, but the moment I get suspicious that something that is hard to decipher has been chosen to cover up some bloated request, or something is not really on the up and up, I become suspicious. And the moment I become suspicious, I want to see an improved proposal 3 months later. So, but yeah, I have some words on that, on implications there as well. Weak scaling is the other experiment that you can do, other type of experiment. Now the workload is proportional to the number of resources. So you do workload X on 1 node, you double the workload, and you go to 2 nodes. Now, ideally, your execution time would stay constant. In reality, of course, it goes up a little bit because there will be overhead most likely. And now if you plot the ratio of T1 over Tn, that is the parallel efficiency. Now, in that setup, parallel efficiency is ideal efficiency is 1 and non-ideal is lower than 1. And here on the y-axis, you use a linear scale, and on the x-axis, you may use linear or logarithmic scale for the node count, depending on how many orders of magnitude your test may cover. It's really often done for larger calculations on multiple nodes, on hundreds of nodes, thousands of nodes. Just a side note here, in some fields it is common to use progress rather than execution time. So for example, in molecular dynamics, the progress is measured how many femtoseconds of simulation can you do per second in the real world. That is all fine. If you use such a unit, just add the sentence that explains it. If your proposal is reviewed by somebody who is not in molecular dynamics, that person will struggle for a moment. What does it mean, femtoseconds per second? So it's always helpful to explain it a little bit. But it's perfectly fine to use a little bit of the lingo of your field. Just be a little bit more verbose about it when you do that. Same as for time steps per hour. And this is how a weak scaling plot may look like. Nodes here, parallel efficiency, ideal is 1, and then you get a curve like that. Or sometimes you get a curve that is just never really flat at the beginning. It is just a decreasing line. That is fine too. Yeah. And so basically your parallel efficiency is ideal time versus over actual time, really. Pretty easy. So this is how those two look together. Hands-on advice, use common sense when picking a target number here for the x-axis. Particularly for large calculation with high SU consumptions, do not target quick completion at the expense of efficiency. The goal here is that you know how to run the code. That's kind of a side effect. And then that you know how to pick the number for a certain experiment. And of course, reviewers know that later on you will run other experiments of a different size that require a different node count, and will hope that you will pick then the node count accordingly. The review panel is not overly concerned with wall clock time. There's a caveat, comes later, but for now we are not concerned. The award period is typically for a year, and you are expected to run through the whole year. So you cannot make the argument, it's so much more convenient. We burn a few more SUs to finish in the first 2 months, and then we have 10 months for the analysis. That's not a good idea. If you have a small allocation at the end, then of course you can push more jobs through and you can get done before the year is over, but in your consideration for the estimate, you should not use that argument. And we all know non-scaling is a fact of life. Just find a good compromise and present your data, of course, in a favorable way, but be transparent. Don't make the reviewers suspicious. Balance efficiency and runtime. Stay on the efficient side. Do not push for early completion. Reduce the wall clock time by advancing multiple calculations simultaneously, if that is applicable. It actually turns out that there are only a few groups who have really one large calculation that basically cannot be parallelized that way. For very long calculations, also consider the time in queue. Consider at least 24 to 48 hours of queue time for every 24 hours running. For time-critical projects, there are some special considerations, and of course, reviewers take that into account. So if you do weather forecast, for a forecast that is used in the real world, for example, directing planes to monitor severe weather somewhere, then you can push the limits a little bit more. But at the moment, I would say when you want to use 2x more resources just to get the reduction in wall clock time by 20%, even for these time critical projects, you are really already in very dangerous territory. If you push into inefficient territory, you will be told to optimize your application. And I would say if you're lucky, you're rejected, you only have to wait 3 months. If you receive a severely reduced allocation, then you have to live with it for a year. There are, of course, many of you who do small but numerous calculations. Those have, of course, also a place on a supercomputer. But here, your requirements are a little bit different. Now, if you do single core jobs or calculations that span only over a few cores, now you will demonstrate that you can bundle all these calculations on a single node, because these nodes are not shared on many XSEDE at many XSEDE centers. And now you will investigate what is the best parallel setup. How many nodes per individual calculation do I use? And then how many can I pack onto a node? Memory requirements and speed comes all into play there. Reviewers want to see that you have investigated that. What is meant by bundling calculations on a single node? I imagine you start a job, you get a node, the node is not shared, you're owning the whole node. Now your calculation only uses 1 core, maybe serial code, but the node has 48 cores. Now you ideally would bundle 48 calculations into the same job, each calculation using a different core. Otherwise, you would only utilize 2% of the resource and not 100%. I hope that answers that question, Nick, but we can get back to that. Machine learning, of course, special considerations there. Yes, inefficiency can mean anything, but in particularly what you are describing there, Kai, you want to use a large number of CPUs, but the code doesn't scale to that point. That would be highly inefficient. Okay, machine learning. That the game is a little bit different. You will most likely use a well-known package that all of us know, but at least mention which one and describe some details. But they are, of course, the packages are well known. Now, machine learning has 2 parts. There's a training effort, and then there is the application. For the training effort, it's a more vague process to estimate how many SUs you may use there. So some creativity is in order, but the creativity is not, you kind of know it's difficult, we want just some number. Describe, for example, what time it took on other projects, on previous project, on a smaller project, something like that. It's admittedly vague, just be creative, put something there. When you apply your learned model to something that may be or should be more straightforward, because you can know how long does it take to apply your model to some input data set. When you do that, you will most likely target GPUs, but target single precision GPUs. We have a lot of clusters that have dedicated hardware for machine learning. Those are single precision GPUs. They are much more cost effective than double precision GPUs. So target that. Handson Advice, machine learning is different. Stuff is different. Scaling is a vague concept there. Software is well known, but explain it a little bit, which one you're using, what your workflow looks like, and then estimate the SUs from there. Let me fix a typo. Reviewers are aware of that. Other slide, special considerations, double precision GPUs. I'm taking this from a non-XSEDE system from Frontera and Longhorn. If you do what I would call traditional science, that is not machine learning, most likely you will need double precision. You will be on a different type of GPU. These GPUs are very, very expensive, and for many applications, their speed advantage is unfortunately not very large. So you have to take that into account. From Frontera Longhorn here, you can see how expensive the hardware is. We have Power 9 nodes with V100 cards. That is a very, very typical setup these days. 4 cards plus 1 node, and you can see that the charge rate is 6x. So we are charging 6 SUs per node per hour. On a normal node, we charge 1 SU. So node for node, your code has to perform 6 times faster on 4 GPUs to be even on the SU charge scale. And so me personally, as a reviewer, I always appreciate it if there's some performance comparison. For many codes, the speed up is not much higher than 1.5. In XSEDE, situation is a bit more muddled. I like to ding my colleagues here a little bit. Some of them do not understand the units. They are stuck to the old concept of core hours. We use node hours, and then a node hour on a normal node is roughly the same cost as a node hour on a single GPU. That makes it a little bit easier. However, if on a particular system they are using core hours as SUs, and the GPUs are of course in node hours, then that's just an additional factor that you have to do. When you compare performance CPU to GPU, you will compare a card versus a node. Then roughly the number of transistors is the same, the power consumption is the same, and importantly, the price is the same. Speed up is not a whole card versus a single core, or an up-to-date GPU versus old CPU nodes. So Frontera Longhorn, those systems came online at the same time. So the 56 cores in the Cascade Lake node are comparing that to V100 is a fair comparison. These bogus statements, we observe a speed up of 64 or some number. Usually they come from comparing a card versus a core. Not surprisingly, a core has 1 to 2% of the number of transistors than a whole card. So how can the performance be the same? If I'm a reviewer and I read these speed ups, I very often come to the conclusion very, very quickly that the user doesn't really know what the performance on the GPU is and how that all plays out. And it often means I want to see a revised proposal. Now, you have done the scaling, you have picked a number of nodes, and you have found an efficient point where you want to run your calculation. Now you use the same data to estimate the number of SUs that you will finally be using. And there will be some very simple math to estimate the total request size. And you take the timing from the scaling experiment plus the extrapolation, and then you come from there. So you present details for all planned experiment. Again, common sense, not for all the super small ones you want to do that are just similar to the big ones. So there apply something, but you have to allow the reviewer to follow your estimate, and that gives the reviewer reassurance that your estimate is not bloated. And me personally, like many other reviewers, we like to see a table. I have one example on the next slide that summarizes everything. If you do parameter study, that is, you do 10, 100 of very similar calculations just to cover a parameter space, you should highlight that you have selected a reasonable or small number of parameter combinations to begin with. And potentially, if that applies, but it applies in many, many fields, that how first results will inform you to select other parameter combinations and how you already weed out parameter combinations while you're creating your grid of data. So don't write that, oh, we want to fill the grid, and then afterwards we throw away all the data that is unreasonable. And another point is, don't forget to justify storage. Don't miss it. It's not a big deal. Very often it is just a few sentences that says this calculation produces that much output per time steps. We have so many time steps. You add it all up. We need certain gigabytes on tape, and that is your storage justification. So let's spend some time on this slide. Let's start with the table. That's a summary table. What experiment you're running, the method, the resolution, simulation time, number of nodes, total runtime, number of simulations, and then you add that all up, you get number of SUs. And of course, as all reviewers do, I look at the large numbers first. And if I see a large experiment here that is implicit 3D, and in the end I'm fine with that, I will be fine with all the smallest or smaller numbers. Here's a different experiment that is a different method, also large numbers, so I will look at that at the same time. So basically your SU count comes from simulation time, number of nodes, total runtime, number of simulations, and then of course, if the unit is not nodes but cores, then there's an additional factor, but that is nothing to worry about. Now, the simple math is up here. Number of nodes or cores, total runtime, number of simulations is equal SUs. Now you use the scaling to determine the number of nodes or cores for an individual calculation. That number is here, and the reviewer can go back and see how that number is in a regime where the reviewer thinks or agrees that's a reasonable number. And so then the scaling and the performance data that you have created will also map simulation time to total runtime. The simulation time is the time you need in your simulation to come to the answer you are looking for. And in the scaling document, in the efficiency part, you can translate that into what is the total runtime it will take to cover the simulation time. So you have determined the number of nodes, and you know each time step takes an hour. I need 10,000 time steps. So how many total, how much total time is that? So number of node and cores comes from your document directly. You use the same data to translate simulation time into total time. And the justification of how much simulation time you need to answer a specific question and how many simulations you need, that comes from the sciencey bits of your proposal, and also the resolution, if that applies. Not everything applies for every field of science. And now you have all the 3 bits here in place, and they all make sense. And out comes an SU number, and that SU number is one of these numbers in the last column. And everything is transparent, and the reviewer can follow that easily. Another stumble, some PI stumble that community codes, well-known codes. Oh, everybody knows the code, they work, and don't bug me. We want scaling for that as well, to see as well. You should document scaling to demonstrate the scaling for your specific setup. Community codes often cover a wide range of numerical setup, and it's not just setup, but also the size. So how many molecules you have in your MD simulation, stuff like that. How many galaxies or megaparsec cube you have in your astrophysics simulation. We want to see the scaling on the target machine, on a machine with a very similar architecture. Kai, I come to your question in a second. So when you present scaling on a different machine, now, of course, you have to apply a fudge factor that translates the performance of the machine where you present scaling to the performance of the target machine. If the architecture and core count and everything is very, very similar, that factor is very close to 1, and we can accept such a factor. But if you come from a machine where a node has 16 cores, and that's an old architecture, and you go to a node that has 48 cores, the factor is much more than 3. 3 is just a node count. And then the factor becomes so mushy that in the end, your total SU estimate may be off by a factor of 2 or 1.5, and that is just not acceptable. So you accurately estimate the number of SUs, and you do that by having a scaling document, and then you do that. Yes, Kai, a resolution is the number. It depends from field to field. Resolution could be number of particles, it could be number of grid cells, it could be in adaptive mesh refinement, kind of a product of cells and cells times particles in a cell, something like that. But it is something of that nature. Okay, so we have community codes. And yes, I almost forgot this one. It's particularly tempting in community code. Everybody knows them, don't bug me. Read this document on the web. We have all done reviews. We do not want to read any external documents. We're happy to read the 10 pages that you provide, and that is it. And so don't expect that reviewers go the extra mile and read a different document or your publication. If you have something published, cut and paste from your publication. Nothing wrong with that. In the end, reviewers want to read about your experience on a specific system and not about something that somebody else did, particularly not what the developers of the code did who are experienced in all these things. And therefore, if you're not demonstrating that here, then the reviewer may assume that you do not know how to run that software properly. Other considerations. Your request may not just about compute as use, storage, long-term usually on tape. There's some medium-term on disk. And then sometimes special queuing demands for very well justified requests. If it is time sensitive, sometimes that's coupled to reservation at certain times of the week or in the day, something like that. But you know, that is only when it's really justified. And also, I highly recommend that you disclose any problems that you may anticipate. You're not penalized for adding special requirements to your proposal. We are just more than happy to work with you before you cause trouble on the system. And very often that is related to file I/O. So that is something you should have an eye on, particularly if you are planning to scale up with a large jump into territory that you have not covered before. Often I/O problems come from that large jump. And the file system is the most vulnerable system or subsystem in any supercomputer. That is where a single user can cause the most havoc and have the most impact on other users. If you kill a node and the node has to be rebooted, the admin will not be happy to do that 3 times in a row, but that's it, you have killed one node. File system, if you kill the file system, everything comes to a standstill. And then sometimes file transfer is also a problem if you have to transfer really petabytes of data from other resources onto an XSEDE storage system. Yeah, I think that's also very important here on this slide. Anything that you have done in the past to improve performance, mention it in your proposal. It just proves to the reviewers you know what you're doing, you're interested in efficiency, and you have already done something. So bragging goes a long way there. So have you done anything of this? Any of these here? Efforts to understand the code and the workflow performance. Have you profiled the code to measure performance? Have you done anything for code optimization or to optimize parallel efficiency, optimize the scaling? And again, anything to understand, minimize, or optimize I/O. Write about your efforts. Reviewers like to read about that. Oh yeah, now almost my last slide. What do you do a year later? You have done your first year with a complete proposal. You have done research. Now it's time for the renewal proposal. At that point, now you are really in the position for the next proposal to provide up-to-date performance and scaling numbers from the actual machine that you have been using and that you will likely target the next year around as well. So at that point, then there's really no excuse to not have any relevant data from the target machine. If you go larger and larger, it becomes also more essential for any proposal. And if you have started from a startup, there will be cases where the startup, the SUs that you had there or the time that you were able to spend on providing the data was insufficient. So now it's time to fill in all the holes. Up-to-date estimates of the SU consumption for the based on the first year. And again, write about other experiments that you have done to increase performance. The quest to increase performance and gain efficiency really never ends. I hope in the first year you have played and explored a little bit the MPI to OpenMP ratio if you're using a hybrid code, or you have played with the binding of the MPI task or the OpenMP threads, or you have gained more experience in bundling smaller jobs in smaller calculations to fill up whole nodes and to bundle those into larger jobs. Anything you have done there, write about it. We like to see numbers on the target machines. The larger the request becomes, the more mandatory that becomes, and it is absolutely true for homegrown codes and for community codes. And that is my last slide, my summary. Design your proposal around the computational plan. Use scaling as a proxy to demonstrate efficient use and to demonstrate that you know overall what you are doing. Use detailed basic math to estimate the total SU time. Be reasonable with your request size. Ramp up over time. Know that it is a tough competition. Some effort, a little bit of effort goes a long way. And of course, present all your data in the most favorable light you can. Just don't go beyond the point where it looks suspicious. And that is all I have for the moment. Thank you very much. Christiana. Oh, I should really add that on one slide. We want to read one proposal per research group. If we allow several proposals per research group, the number of proposals would triple or quadruple. One proposal per research group. And so if you are leading a group, your postdocs cannot have their own proposals. This has to be all rolled into one proposal.
Right. I'll follow that up with what Lars says, Christina. So even in the rules of the submission page, it will not allow another or multiple proposals to be submitted by the PI, and so we check this pretty closely, and it's really to take the pressure off of you as a research group of writing multiple proposals, and also our review panel of reviewing so many. I mean, at 200 per quarter plus, we've seen as high as 275 proposals in a quarter. That puts a big burden on our review panel. So
let me add little bit of information. You can be, of course, the PI on one proposal and the co-PI on a different proposal. But the proposals have to be different. It has to be a different scientific question that is being solved. You cannot be the PI on two proposals, but you can be the PI and the co-PI. There was a question from Nicholas. Are we expected to provide both weak and strong scaling? No. You're provided to provide data that allows us to judge efficiency. And one of those scalings is recommended. There are corner cases like machine learning, where it's a little bit different, but yeah, only one of them. Whichever is most suited to your application.
I'll handle that question from Alessandro. So I think you're following up the question from Christina. So yes, we would recommend that you, if you have multiple projects, you give us a justification or a breakdown, project 1 or project A, project B, project 2, however you're going to do it. And then you would also give some scaling estimated SUs and all for those different projects. Maybe project 1 is using NAMD and project 2 is using OpenFOAM. So we'd want to make sure that you're using both of those codes efficient for the different projects, and then break it down in a clear justification section of project A is going to need this amount of storage and this amount of compute resources, and project B would need, similar storage and whatever. So it's there's some examples out there on the allocation website. I'll put the URL in the page here. Let me grab it here real quick.
Yeah, posted in the chat, and I handle the next question from Caroline. Yeah, machine jitter, that's a good question, but usually we don't worry about it. The jitter is really not that high. There are several reasons for that. So you plot your performance curve, and then you see, is there an outlier, and you may run that calculation again. But we don't want a statistical analysis of multiple nodes, multiple runs, and then what the jitter was. And also, if you really scale out, at some point, you just don't have enough SUs to run the same experiment multiple times. And the third minor point is, some people run, of course, a couple of time steps, and from within the distribution, within the same calculation, what the time steps, how they differ, you can estimate a little bit the jitter of that. But usually you just run every calculation for your scaling documentation once, and then if you're suspicious, or for the very small ones, you run it multiple times to convince yourself the jitter is really not that high, and then that is.
So Christina, your question, the follow-up question, so your first year, you would want to ask for what your team plans to do for that particular year or that upcoming year for that submission. And then, the second year, you can continue to add additional projects if they're necessary, or continue the prior project that you were using. But you're definitely, we're going to want to stick to one proposal unless they are so different. And some people say, well, this is astrophysics of this or astrophysics of that. And well, they're still astrophysics in a sense. But if it was, a social science project or a gateway that you're working with, and then on top of it, you have a research project that's in a completely different field of science, then we would consider that. But you'd want to chat with us beforehand. So we'll have to actually help you do that submission of the second proposal. So just let us know. I mean, if you have questions, again, you can always send email to help@xsede.org, and Jay, Lars, or myself, or one of our teams can definitely get back to you and have a chat about this.
Yeah, let me answer in a slightly different fashion, because you asked if that was preferred. My answer is, if your request for project A is already very large, and you bump into the territory where size becomes a question, and you can do project B then a year later, then do project B a year later. But if these are both sizes are not significantly large, and you have the manpower and the desire to tackle both projects in the same year, by all means, put it in one project and get started on put it in one proposal and start both projects at the same time.
Also, let me follow up another part of a question here. So Lars commented that you could be a co-PI on another project, but a PI on one, and that is definitely acceptable. There is a section both in the main document and on the submission form of disclosing your access to other HPC resources or other grants. And this is important to disclose this. As I say in the webinar I do about writing and submitting proposals, transparency is key. If the reviewers have some sense that something is not fully disclosed here, and then we go digging, we don't want them to have to do that, but we also don't want to be unanswered questions, and then this puts doubt in their mind, and then it could possibly lead to a rejection, and then you have to wait another quarter to just fully disclose this. So definitely disclose it. Let us know that if you're a co-PI or you're working on another project. We will see it. If it's all part of XSEDE grants or multiple grants, the reviewers have access to see many of these other proposals or ones that you're collaborating with.
And of course, there are so many resource providers and reviewers. We know about other systems, like Insight or Frontera, or, so if there's overlap, be transparent.
Right. So Christina, that would be great. We'd be happy to chat with an email and all. But you talk about running out of resources. There's always the option to submit a supplement. Supplement's going to require you to give some more of these details. If it's the same work, you just run out of service units for that project. You can repeat a very similar main document, the code performance sailing. You'll be required to put in a progress report so we have some understanding of where you are in the process of that period of allocation. But supplements are always available to do. You're allowed to submit them. It'll be up to the site or the sites, the resource providers, to be able to accommodate your request in full or not. So, but definitely send email to help@XSEDE. We can chat, or you and I and others can have a separate call and chat about your team's situation.
Yeah, the slides are available, and of course we can send you a PDF, a copy of the PDF.
And we're recording this session, so I think it was a nice session. We will probably make this one available on the URL that I listed there before, the XSEDE Portal Allocations research page. There's one out there now if you want to see that. It's a couple quarters ago, I think, but this one went well, so we can put that out there. But that'll be up to Dr. J to pull that together and get it uploaded. You're welcome.
Any more questions? No, if not, then I think we adjourn. And
if you have any along the way, always, again, send email to help@xsede.org, and we'll be happy to answer those. Remember, there's a submission period ends October 15th, so you have 3 weeks roughly, I think, to get your submission in. And then if you're not ready for the October 15th deadline, that repeats itself the next quarter. So the next deadline would be December 15th through January 15th of 22.
Okay. Did you stop the recording?